okay, so bivariate data is data with two variables. That's bi means two, variate means variables. So two variables, so two values, amount of lions in the park over years. So years is one variable, amount of lions are the other. Scatterplot is data that plots, or it's a graph of the data plotted as a collection of points. So you take the two variables and plot them together. So a correlation is the relationship between the variables. So if you have a positive correlation, the dots look like they're moving upwards. If you have a negative correlation, the dots look like they're moving downwards. And if you have no correlation, the dots are just wherever. Okay. A strong correlation occurs when the dots are close together and they mimic a straight line. They're narrow. And a weak correlation occurs when your dots are kind of wider, but they still show a positive or a negative trend. And then we had discussed correlation versus causation. Okay, you can have a correlation, but it not be a cause. For example, population. Population grows every year, right? Every year there's more people than there were the year before. And so you can plot the years and you can plot the population, and there's a relationship, there's a correlation. It's a positive correlation because as time passes, there's more people. But it is not the fact that it's a new year that causes there to be more people, right? Time passing does not cause more people to exist. The things that cause more people to exist are longer lifespans, you know, better health care, so people tend to live more. So then there's more people. So there's a correlation between time and population, but time does not cause population. Does that make sense? Okay, so a line of fit is a line that approximates, so it's a straight line. That approximates the shape of the data. I'm going to go back for just a second. So if I came to this positive correlation right here, and I drew a line like that, that line fits the pattern of the data. This would be my line of fit. And there's more than one line of fit because they're, you know, it's your opinion. Does this line, maybe you would want to make it a little steeper or a little flatter. You just wouldn't say, here's my line of fit, because obviously that does not fit the data. So, so the line of fit fits the pattern of the data. And then we use that line to write the prediction equation. So this is the equation of the line of fit. And we determine the prediction equation by finding 2 points on the line. And then you find slope and y-intercept. And that gives us the equation of the line. And that equation, that prediction equation, it's called a prediction equation because we can use it to make predictions. About future events. Okay. What we want to do is we have a table showing the percent of U.S. households with at least one personal computer since 1984. And what we do is we take for our our years are the independent variables, so that would be x, and this would be y. But we want to make our x actually the years since to give us a point of 0. So 1984 will be 0. 1989 is 5 years later. 93 is 9 years later. 97 is 13 years later. 17 and, bless you, 19. Bless you. All right, so we're going to take this years since 1984, we're going to plot that on our x-axis, and I'm going to put that up top because there's not room down here. So we have 0 years, so we need to go up to 19. So I've got 1, 2, 3, 10, 11, 12, 13, 14, 15, 16. So I can't quite do, I'll do by 2s. So this would be 4, 8, 10, 12, 14, 16, 18, 20. And then our y-axis is the percents. So I'm going to start down at the bottom for this, and I am going to go up by maybe 5s because we have to go up to 60. So I've got 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60. So that'll work. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55. Okay. So this is years since 84, and this is percent of computers. We now want to plot these points. So at 0 years, I'm at 8.2%. So here's 10, here's 5, 8.2 is somewhere in the middle. Does not have to be perfect. All right, so 4 years, we don't have a point for, but for 5 years, we're at 15%. So 5 is, we're going by 2s, right? So here's 6, so 5 is halfway between 4 and 6, and we're at 15%. So that would go right here. At 9 years, which is halfway between 8 and 10, we're at 22.8%, and 22.8% is halfway between 25 and 20. Then we are at 13 years, and we're at 36.6%, so that's going to be right above 35. At 17 years, we're at 56.3, so that's going to be right above 55. And then at 19 years, we're at 61.8, so that's going to be right above 60. Now you can see that if you actually drew the line connecting these dots, it wouldn't be a straight line. It would be sort of like a curvy thing. This would be the line of the actual dots, but we're not going to use that line. We're going to make a straight line to be our prediction line, our line of fit. So what I'm going to do is I'm going to try to draw a line that approximates the data. And what I want is I want about the same number of dots on top as underneath, and I want them about equally distant away from the line. So if you look here, I have 3 dots on top, I have 3 dots underneath, and this line, to me, approximates the data. Now, everybody's line could be slightly different. Not everybody will draw the same line. As long as it looks like it approximates the data, you're fine. And we're going to find 2 points on the line, and here I have 2 points exactly on the line. This point, here, let me actually, is 2 years since and at 10, so we'll be 2 years, 10%. And this point is 6 years, 20. although those points are kind of close together, so I might actually come out here. And do 20 years, 60%. So I get a further spread. It's a matter of opinion. I could have done, any number of points along the way. So if I do 60, 20, 60, and 210, let's say, I'm going to first find my slope. Okay, so I've done the scatter plot, I've done the line of fit, and now I need to describe the correlation. So I made my scatter plot, I made my line of fit. I want to describe the correlation. Positive or negative? Positive. Do you think it's a strong positive or a weak positive? Yeah, it's a strong positive. We're using 2060 and 210. 210. Okay, and I'm first going to find my slope. So I'm going to use my slope equation. So I have 60 minus 10 over 20 minus 2, which is going to give me 50 over 18, which is 25 over 9, or 2.8. That's my slope. Then I'm going to use my slope and one of these points, and I'm just going to use the smaller point because it's nicer. And I'm going to plug that into, hold on, y equals mx plus b. So I have 10 is equal to 2.8 times 2 plus b. So 10 is equal to 5.6 plus b. And I'll subtract 5.6 from both sides. And I'll get 4.4 is equal to b. Alright, so we've got our equation now because we found our slope and our y-intercept. And we're going to predict the percent of households in 2012. So first I need to figure out how many years past 1984 is 2012. So this is 28 years later. So I'm going to plug that in for x. So I have 2.8 times 28 years plus 4.4. So in 2012, our prediction is that 82.8% of households would own computers. Our accuracy. We come back to our previous page, and at 19 years past, we were at 61%, right? 61.8. And if we look at how much the percentages are kind of on average jumping, there's a big jump in this area, but that's because computers were gaining popularity and they were getting better. But here there's about a 5-point spread, and that's over a period of 2 years. 5-point spread over 2 years. Well, if we come to 2010, that one we just looked up, that was 77%. If we added 5 to that, we'd be at 82. So we're pretty accurate. So looks good. This time we have average selling price of a new privately owned single home. I don't know how accurate this actually is, but it's in the thousands, so this would be 154.5 thousand, so 154,000, 166,000, 181,000. And then again, we're going to do years since 1994. So we'll do years since 94. So this will be 0, 2, 4, 6, 8, 10. Okay, and then we have our price in the thousands. I've got 1, 2, 3, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay. Okay, so it looks like I need at least 7 in between each bar. Did you guys catch what I was doing there? Okay, so I'm gonna make them 10s. And I'll start at 150, 160, 170, 180, 190, 200, 210, 220, 230, 240, 250, 260, 270. Okay. So I've got my scale. And I'm going to start plotting them. In 1994, which is year 0, I was at 154.5. So here's 150. Here's 160. 154.5 is about halfway between. 2 years, I was at 166.4, so that's probably there-ish. 4 years, I'm at 181. Well, if this is 180, so that's going to be just right on top of 180. At 6 years, I'm at 207, so that's probably there-ish. At 8 years, I'm at 228, almost 229, so right under 230. And at 10 years, I'm at 273, so here's 270, so I'm going to go above that. Now I'm going to make my line of fit, and you can see I wouldn't want to just connect these 2 dots. Oops. I wouldn't want to just say, okay, do that, because then I have all these data points underneath here. That's not a good line, right? That's probably the best line of fit right there. Well, no, I was going to say because I've got 3 points on each side. You can see this is kind of a curve, so it's tricky to get a good line of fit, but somewhere where I have 3 points on one side, 3 points on the other. And I probably want to do that because these 2 are so far away and these 3 are really close, so I probably would go through this 1 point for sure. Again though, it's anything in this sort of general area is going to be okay, just provided you're not drawing some line, you know, over here and saying here's my line of fit. That's not, you know, as long as it's mimicking the pattern, there's not one exact correct line. So I'm going to use this point, that's this data, so that's 1 point, and then I'm going to find another point, and here's a good point right here, and that would be 9,250. So I'll say 250 minus 166.4 over 9 minus 2. This is for my slope. That's 83.6 divided by 7. So I get 11.9. What this means is we're basically, the house prices are going up about $11,000, $12,000 per year on average. And then from there, I'm going to find my my prediction equation. I need to find my y-intercept, and we used y equals mx plus b last time. Does anybody want me to use the point slope where you have y minus y1 m times it? Nobody? Okay. So we use y equals mx plus b again. So y is 250 is equal to m times x, which is 9, plus b. So 11.9 times 9 is 107.1. And if I subtract 107.1 from both sides, I'll have b. So 142.9 is b. So my equation is y equals 11.9x plus 142.9. And if I want to figure out how much a new home should have sold for in 2010, I'm going to take 2010, that's 16 years from 1994, and plug that in. So it should have been $333.3 thousand that a new home sold for in 2010 on average. We have a parent function, and the parent function, hold on, let me write first. First of all, we have graph families, and those are functions that their graphs, the pictures all look similar. So we have straight lines. A straight line always looks like another straight line. They just might be pointing in different directions. One might be positive, one might be negative, but they're all straight lines. So every linear function is in a family. And the family is that they're linear. We have parabola functions. We have absolute value functions. So we're going to do absolute value only from this section. And the absolute value function is y equals the absolute value of x, or you could say f of x equals the absolute value of x. And then you have variations on this. The parent function of the absolute value is y equals absolute value of x. The type of graph is V-shaped. The domain is all real numbers. The range is all non-negative numbers. Bless you. Or you could say y is greater than or equal to 0. The intercepts are 0 and 0, and it is not defined when y is less than 0. So here's why you get a V-shaped graph. If I plug 0 in for x, I get 0. If I plug 1 in for x, I get 1. If I plug in -1 for x, the absolute value of -1 is 1. Absolute value of 2 is 2. Absolute value of -2 is 2. 3 is 3. -3 is 3. So as I plug in absolute values, I just keep getting positive answers for every positive or negative I plug in. And so I get, if I drew it correctly, I get a V. And it goes on forever. So the domain is all real numbers because I can plug in any x. And pick any x I want, plug it in, positive or negative, but the range is limited. Because I'm plugging in numbers and I'm only taking positives out, my range is limited to only positives or 0. Because absolute value can never be negative. And so it's undefined. When y is less than 0, there's no graph. There's no such thing, so it doesn't exist down here. It's undefined. And this is the parent function. So every absolute value graph, no matter if I put a 2 on the outside or add or subtract things to it, multiply it by stuff, they'll all be V's. They just might be V's that have been moved around or flipped upside down, but they'll all look like a V. What happens when we change the parent function? I've multiplied the x by 2 and I'm going to subtract 4 from it. So the easiest way to do this is to start graphing these is to just make a table, x and y. F of x is the same thing as y, so you could put that in there if you wanted. And if I plug in 0 for x, I get 2 times 0, which is 0. And then I take the absolute value of that, minus 4, so I get 0 minus 4, so I get -4. Which reminds me, I need to put some axes on our graphs. So just put some axes on there. So if I plug in 1 for x, I get 2 times 1 minus 4, so I get the absolute value of 2, which is 2, minus 4 is -2. And I usually like to, as soon as I get a couple points, I like to go ahead and start plotting them so I can see my shape emerging. So at 0, I'm at -4. At 1, I'm at -2. So let's see what happens if I plug in -1. I get 2 times -1, which is -2. I take the absolute value of that. That's +2 minus 4 is -2. So at -1, I'm also at -2. And if I plug in 2, I get 4 minus 4, which is 0. So what do you think happens if I plug in -2? 1 gave me -2, and -1 gave me a -2. 2 gives me 0. So -2 should give me 0, yeah. So now I have my pattern, I have my V. So now I can come in and I can make my V. And you can see it's still V. This V is skinnier. and moved down. My domain will not change. I can still plug in any x I want. So my domain is still all real numbers. Now my range has changed. If I look, my range is my y's. Here's where I stop. I have no y's below -4. So -4 is my lowest y, so my range is y is greater than or equal to -4. Because I have every y going up, I just don't have any y's going down. So I find that spot, and that's where my range starts. Do the same thing. I can make an XY table. If I plug in 0 for x, I get 0. No such thing as -0. Plus 1 is 1. So I get 0, 1. If I plug in -1 for x, I'm going to have the absolute value of I meant to plug in a 1 first, sorry. Positive 1. I have negative the absolute value of 1 plus 1. So I have -1 plus 1 is 0. If I plug in -1, the absolute value of -1 is 1, and then I make it negative. So I have -1 plus 1, so that's 0. If I plug in 2, so right now I'm here and here. Negative absolute value of 2 is -2, plus 1 is -1. And if I plug in -2, I'm going to get the same thing. The absolute value of -2 is 2. Make it negative, I get -2, plus 1 is -1. So I still have a v, but now my v is pointing the other direction. And that's because of this negative right here. It flipped my absolute value. Made it flip over. My domain is still going to be all real numbers. That's not going to change. I can still plug in any x. That's the symbol for all real numbers. My range is what is changing. I now don't have any y's above this point. So here's the point where my y's stop, and they're all below that, so my range is going to be that y is going to be less than or equal to 1. So we already talked about families of graphs a bit, but they're groups of graphs. That are similar. So they look the same. And then the parent function is the simplest of the family. So a constant function is where you get f of x equals some number, or y equals a number. Okay. So it's just a flat line. And the parent function of it, sorry, is y equals 1. Put that in the wrong space. The parent function is y equals 1. And y could equal to anything. Y equals -3, the line would move down here. It's a flat line, and it just moves up and down the y-axis depending on what number it's equal to. Okay. The identity function is a linear function, and it's y equals x, or f of x equals x. And when that occurs, we get a straight line with a slope of 1 and a y-intercept of 0. So it's essentially y equals 1x plus 0. That's if you kept it into y equals mx plus b and you had everything in there. So this can change by changing the slope or changing the y-intercept. But it's basically any straight line. That's not this. So we don't have any flat lines and we don't have any straight up and down lines, because this is not a function if it's straight up and down. But it's any line that has a slant, basically, any slanted line. Absolute value function we just talked about. That it's not the constant function, and it can't be a straight up and down because this straight up and down line is not a function. But any other line is part of the identity function. But the actual identity, the parent function, is y equals x. For absolute value, the parent, we just talked about that, is a v. Actually, let me get rid of those arrows. And the parent function is f of x equals the absolute value of x, or y equals the absolute value of x. And so you have a v starting at 0 with a slope, basically a slope of 1 or a slope of -1 on this side. But you're just going up 1 each time. Up 1, up 1, up 1. And then you have the quadratic function. This is x squared, or y equals x squared. This occurs when you square the x and you don't get a v, you get a curve or a u. It's called a parabola. And so it's a parabola with the vertex at 0, 0, and it's perfectly squared. So 1, 1, 2, 4, 3, 9, -1, 1, -2, 4, -3, 9. So you're squaring the x every time. With your parent functions, the domain on these is not going to change. The domain will always be all real, so I can always plug in any x. The thing that will change is the range. So on the constant function, the range is whatever number the line has moved to. On the identity function, pretty much the range stays all reals. On the absolute value function, the range changes based on what has happened to the v. Is it moved around? Is it moved up? Is it moved down? Is it flipped over? And the same with the quadratic. The range will change based on, have we flipped it over? Have we moved it up? Have we moved it down? Have we moved it, wherever? So you'll have to look at the picture, or in a moment we'll show you some other tricks for that. First thing is identifying the type of function. Well, if you want to identify the type of function, we look at the picture. This is a flat line, so this is a constant function. What is going on with my pen? Constant function. If the graph looks like a U, it's a parabola, it's a quadratic. If it looks like a V, doesn't matter which way the V is pointing, but if it looks like a V, it's absolute value. And if it's like a slanted line, it's an identity function. Transformations occur when any change is made to the parent function. It can change location, or it can change the size, or it can change the direction. Okay. A translation moves the graph up, down, right, or left. Those are called translations. And so what we have is, hold on a second, I'm going to move that. I'll just work around it. What we have is if k, so if we have some constant k, added or subtracted to parent, so you get f of x plus or minus k, moves you up or down. Okay. If a constant, say h, is added or subtracted to the x before the function, you move right or left. Okay, and that is f of x plus or minus h. So just to give you a solid example about that, H? K. Okay. So just to give you an example of the difference between this, the up or down would be, say, like this, y equals absolute value of x plus k. The right or left would be y equals absolute value of x plus h, like that. So up or down is when the plus or minus comes after the absolute value or the squaring or things like that. Right and left happens when the plus or minus comes inside the absolute value or the squaring. That's the difference. So in this instance, we look like that. Our absolute value, it's absolute value of x, and then we're adding 2 to it. So what this means is I am going to move 2 units up. Okay, so here's what my normal absolute value looks like. This is right here. This is just y equals absolute value of x. This is the parent. Okay, my new graph, I move 2 up. And this is y equals absolute value of x plus 2. So that's my translation. I moved 2 spaces up. When you're adding or subtracting at the end, it's really nice, like this, because that, if it's plus 2, you move 2 up. If it's minus 2, you move 2 down. It makes sense. Plus is up, minus is down. If you're adding or subtracting inside, it's backwards. Normally you would think plus is moving to the right and minus is moving to the left, except it's backwards. So if you add h, so if it was plus 2 inside, I would have moved 2 this way, to the left. And if it was minus 2 inside, I would have moved 2 to the right. So this one is backwards. So just pay attention to that part. This one is exactly as it should be. Plus is up, minus is down. No problem. This one is the one that's a little tricky. So we'll start filling this out now. So if like I said, if I'm adding or subtracting inside, this is h units to the left. So this direction. And then this would be h units to the right. So we'll move this direction. Plus k on the end is k units up. And minus k is k units down. Some more of these. So I've got plus 3. Plus 3 inside means I'm doing 3 units left. So instead of being here, I'm going to go 1, 2, 3, and I'm going to start there. And then I'm going to draw my absolute value parent graph. And the parent graph is always up 1 over 1. So I just moved it over. Now, does it look a little different? Yeah, because I can't go past the end of my graph, right? But if I kept going, it would still be the same V. Here we're minusing 6, and it's not inside the square. It's outside of the square, so this is 6 units down. Okay, so I go 1, 2, 3, 4, 5, oops, 6 down. And it's 1, 1, and then 2, 4. So I've got a U. It's way down here. Okay, so a reflection flips a figure over what's called the line of reflection, and so basically it's like you take the picture and you either turn it sideways or you turn it upside down. You're flipping it in some way. Now, most of our reflections are going to be over either the x or the y axis. So if we multiply by -1, so you get negative f of x. It flips over the x-axis. If you multiply the x by a -1, so you get f of negative x, it flips over the y-axis. Okay, so in this instance, here's what the difference would be. Okay, so for this is y equals negative x squared. This one would be y equals negative x squared in parentheses. So it's the x that's negative, not the x squared that's negative. So that's the difference between these two. So because this negative is outside, or it's not in a parenthesis, this is flipping over the x-axis. Okay. So our parent is our parabola that looks like this. This is y equals x squared. That's our parent. Our reflection this is y equals negative x squared. So what I've done is I've flipped it over the x-axis. The negative is outside of the absolute value, so this is going to flip over the x-axis. So I'm going to be like this. And here it's negative x, so this is going to be flipping over the y-axis. So normally my parent for y equals, let me get a straight line. My parent on this looks like this, right? That's my normal y equals x. This is the parent. When I flip it over the y-axis, it's going to do that. Like, so you can see, like, if I took that picture and I flip it around, basically every positive becomes negative and every negative becomes a positive. So this is my y equals negative x. So if I plug in 1 for x, I get negative 1 for y. And vice versa. If I plug in negative 1 for x, I get positive 1 for y. So it flips all of the negatives and positives, it changes them all.